how can we introduce the idea of strategy in our mathematical models of evolving systems, right? What I mean by strategy. In a very simplified way, also in previous lectures, we have seen how to analyze the population dynamics in mixtures of species, each species having one set of attributes usually related with probability of or rate of replication, or the ways in which the different species interact, right? At some point, we analyzed, for example, our first analysis of these kind of systems, two equations for competition. What happens when two populations of cells, for example, compete like cancer and normal cells within an organism? In that perspective, if F1 and F2 are where the population growth rates for each strain, essentially the dynamics was kind of compressed into something very simple. The one who replicates faster than the other, and that was the final result of the analysis, assuming that the total population is constant, right? Something that we use to collapse the dynamics into a single dimensions. The one who grows faster wins, right? In that respect, the dynamics is very simple. No matter where do you start, could be 1/2, could be anything else, right? The one that replicates faster takes over all the system, even if its initial population is small. We analyze that in a number of ways: stability analysis, using the potential function to describe the nature of stable and unstable states. And there was the competition picture. What happened when, for example, I cooperate with the other species? Remember that here we had this dynamical scenario where I replicate, right? But I do, provided that the second species helps me, right? And only in that case I can survive. That forces the system into going into a state of coexistence. And remember, we said cooperation is extremely important in terms of evolutionary dynamics, right? The picture that the fastest replicator, the strongest, it's the one that survives, is just a little part of evolutionary history. In fact, cooperation is what makes many biological systems so robust. And also, we had this different system where the idea was that you have two options that can be chosen by a population of different individuals, right? Remember the example we used for the Betamax versus VHS dynamics, right? You have users, a large population. We assume that you have either chosen one kind of support versus the other, and that there's a population dynamics where if you want, the strategy is to be part of the community that has more individuals, right? Because it's the more compatible one, right? And that this kind of decision makes unstable the state where the two designs, the technological designs, persist, right? That's not possible. And that's what happened historically, that one of the choices was made. It's an amplification process, and it's not rational. So we spoke about rationality, we spoke about population dynamics, and in a way, underlying that, there's the thing that if this is formed by agents that can have a repertoire of behavioral patterns, one general question we can ask ourselves is, how can I make mathematical models that introduce more complex strategies, right? Meaning what, right? An example of that, and we will discuss that in this lecture, is, for example, when you have cells in a population that use different strategies for survival, right? Take one example that we will consider. Imagine you have a population of cancer cells within a tumor. We just consider right so far that all the cells behave the same. But we already mentioned also that within cancer populations, within tumors, we have a high heterogeneity. And you can observe different strategies, right? Because cancer cells have been mutating And using the large space of genome possibilities, you can actually perform different functionalities. For example, you could have a population of cancer cells where some of the cells, right, are motile, can move around, right? They have this possibility. So they replicate with some fitness, let's say FM, but they also move, okay? So that's my XM strain. I have motility, all right? And I have another population, more typical of what we discussed in our previous lectures, in particular on cancer, right, that they replicate. I'm going to write down this here, a thicker line. This is the XR compartment, replicating cells, FR. Why this distinction? Well, here is the nice, interesting thing here, the trade-offs that I have, the payoffs that imply using different strategies. If I move, right, if I move around, that implies a cost. I have to use part of the cell machinery to actually change the shape of the cell and move around. Very important strategy because I might be able to actually gather resources from far away the tumor. Remember, we mentioned at some point that, especially in solid tumors, at some point you are taking a lot of resources. You need to vascularize the system, right? But escaping from that can be a big advantage, right? And it's connected with other phenomena that we have pointed out at some point, like metastasis. But there's a cost of that. That means that if I move, I'm not going to be so fast replicating. The other strain, on the other hand, in this simple picture, right, can replicate faster because I'm not investing anything else. I don't move. I don't need to go around. I just stick together with other cells. So, under what conditions this could be a good strategy versus this, right? Now we can think in strategies. Because maybe if I'm in a context where I'm not surrounded by many other cells, moving is interesting. Moving, it's possible, and I can look for resources. But if I'm in a crowded environment, so if I have many other cells, maybe it's not a good strategy, right? Think about what we use to define how good is a given strategy, the fitness, right? Remember when we studied fitness landscapes. So the fitness of this population, or this population, will be population dependent. So strategies here are more difficult to describe, okay? So first step, how can I make a more general approximation to this framework, right? That includes everything that we already have seen and more things that we haven't, okay? One way of doing that is just writing down very general equations. So imagine that I do the following. What is my strategy for interacting with the others, okay? And I'm going to go for the crucial point here, defined here, game, right? Game theory. Right, in general, that would be some function of the populations, right? Remember that this is my term that includes essentially the competition. There's always be competition if the full population is limited, all right? Similarly, I'll have this here, okay? And F1 and F2, I'm not going into any detail now, it's just general functions. One of the interesting things of this lecture is actually seeing how can I actually assign to a given strategy a number. I'll have a matrix, it's called the Payoff Matrix, that allows me to actually write down strategies in a consistent way. I'm just going to go into a specific result here, mathematical result that I want you to show you. I keep using the same constraint. Remember the constant population constraint that we use all over the course to use just one-dimensional models, right? And following the logic that we have used in previous lectures, what I can actually show easily, right, is that if I take, for example, my first variable, remember that you always can collapse that for x1 because x2 is just 1 minus x1, right? I can show easily that this actually is described by a single differential equation, more complex than the competition version that I have here, but essentially it's the same philosophy in terms of the derivation, right? With this kind of logistic part, right, that is affected by this, right? But now, of course, the form of the mathematical model is in general more complex. Well, first thing I would like to know, what about stability? It's something that general I can say about stability. Remember that in these models, we have a set of points, right, that belong to the domain where I'm, if you want, the domain of real space that I'm considering. Usually, as you know, population dynamics, positive populations cannot be negative, where essentially this collapses into 0, right? If you want to make it compact, when this is 0. I have a set of numbers. What set is going to be that, right? It's not difficult to see that actually have 3 points max, right? From here, clearly 0 is a fixed point, right? Clearly 1 is a fixed point, not surprising, right? These points appear for these two-dimensional abstractions as extreme cases, right? And luckily, there might be an intermediate point, right? Not in the competition scenario here. We just only have 0 or 1. But in general, we'll have some value between 0 and 1. The stability of this value is defined by what? Can we make a general derivation here? Let's make it briefly. Right? Remember that to actually characterize the stability of any point in my mathematical models in the one dimension, right? I calculate this is my function that defines the dynamics, will be the derivative over x of what? Of all this, right? Let me write it this way. Okay, remember that I do the derivative, I evaluate in the fixed point, and the sign decides if it's stable or not stable. And I want to have an expression that I'm going to use afterwards, and you can test with previous examples, that tells me when this intermediate point will be stable or not. Okay? All right, I use this compact notation, right, to address this. Okay. Of course, this all collapses into just x1, but nevertheless, what I'm going to do is to do this derivative for this part here. I just have 1 minus 2x1 multiplied by this. Let me write this way. This is always evaluated at a fixed point. So this is, let's write this here, okay? Evaluated at x star. For x star, I mean x1 star, x2 star, right? Then I take this and I do the derivative of this, meaning that I have this minus this, okay? Again, evaluated at the fixed point. So that's what we have. One good thing, sorry, this is a plus. One good thing of this part is that for the stable equilibrium, this is just 0, so you can forget about this part here. And what remains is this here. And the question I'm asking myself is, under what conditions this is going to be less than 0? Remember, that's the condition that impose on lambda so that the fixed point is stable, right? That's my condition for stability, but I'm almost there. Look at this. This is evaluated, all this, at x star, whatever the value is between 0 and 1. Since it's between 0 and 1, this here is going to be some positive number, right? I know that. For x star, is going to be positive, right? What about that? Well, that depends, right? And in fact, the final result is that this condition leads to the following condition for stability. Let's write down everything. If this is less than this, right? Always, this will be numbers evaluated here. Okay, my intermediate state, right, which is going to be the interesting one, remember, cooperation, symmetry breaking, etc. That is the condition for stability of x1 star, right? Condition for stability. Well, this is a mathematical result, and one of the things that you can actually do, but let's see first the examples we'll consider, is to actually test that these kind of results are a generalization of what we saw step by step, example by example, for each case study, right? So this is the kind of the general formalism. And again, since we want to actually apply this for more general cases where what we call strategies are in place, okay? What we want is to actually define the right formalism. So we would like to know, what about F1 and F2? What can be actually implemented here? And how, given a problem, how can I actually define the right functions? This is part of a general problem that has been extremely successful within both the social and economic sciences and eventually in evolutionary biology. Well, the original formulation of that was due by John von Neumann. You have already heard about him. He was one of these extraordinary mathematicians of the 20th century who contributed to all kinds of areas from quantum mechanics to different areas of computing. The architecture of computers we know is the von Neumann architecture. And one of the things that he actually formalized was the concept of a game. How actually you convert a strategic game, which can have a lot of different important implications, into something that can be described mathematically, okay? And he has a very famous book along with Oscar Morgenstern, which is about the mathematical theory of games. Let me give you an example of how general is this and the kind of problems that we can actually address. And you'll see why it's interesting in terms of both very important problems related with, for example, cancer evolution, or in general context, in general for evolution and even in social sciences. And we'll see how to formalize. The example I'm going just to mention now is so-called the prisoner's dilemma. The prisoner's dilemma is a classic in game theory. I know it doesn't sound like evolution or biology, but it's more deep than that, actually. Imagine the following case scenario. You have two thieves. They have been caught by the police. They have done some criminal thing, right? Robbery or whatever it is. The police has caught them. They have put them in different rooms to interrogate. They're completely separated, right? And they don't have proof of the crime. They just have a strong suspect that they have done something. So they offer them the following treat. If you cooperate with us, with the police, right, you help us, and you say, my colleague did the crime, right, we'll be nice with you, right, we'll be in jail just 1 year, all right? If you don't cooperate, okay, you'll go into jail for 10 years, all right? But of course, the police is offering the same to the other member of the band in the other room. So what do you do? Because the thing is that if I point to my colleague as the one who did something, right, I'm cooperating and having a less charge, right? If we both cooperate, right, we'll both, assuming that we have done a crime, right, and we'll be charged also, but we have cooperated. So there's an equilibrium here. How will you act? The thing is that if you blame your colleague, you have cooperated, and if he didn't act against you, you'll just essentially go free soon, and he will go in jail for a long time. So what do you do? If you both cooperate and you both point to the other, you go to jail for an intermediate time, say 5 years, right? Because the crime has been admitted. So the interesting thing here is that if you calculate, the best strategy for you is to defeat. So I'm going to say that the other one did the crime, right? So I'm not going to cooperate with him. Interestingly, this dilemma suggests that within evolution, and you have confronted with that kind of trade-off, you will essentially always be selfish, right? So why is not being selfish this usual strategy between humans, right? Why cooperation works at all if these kind of dilemmas appear again and again? So one of the interesting results of evolutionary game theory, and we'll discuss a little bit because it goes beyond the mathematics here, but belongs to the fitness dynamics that we have discussed in previous lectures, is that if you are able to repeat the process, if that situation is going to be something that you find again and again, not just once, right? Cooperation is the stable strategy, right? So against the intuition, being selfish is not what agents will choose if they have several opportunities of doing so.